So let's get started. Let me start giving you a summary of what we have seen in the last few classes. We'll start with the summary. And the summary is the following. So you create a vacuum inside a working chamber. That's a vacuum chamber. I said the mean free path is a very important parameter that determines the rate of deposition. So for those thin film growth processes that require only vacuum inside the chamber, no presence of gases, large mean free path means good amount of deposition in a given time. So 10 raised to minus 6, 10 raised to minus 7 torr of vacuum is required if we deal with deposition of metals, alloys, intermetallic compounds. Because you need a completely gas-free and oxygen-free environment. So these vacuum levels also ensure that the mean free path of these emanated particles or atoms reach the substrate without having to collide with the gas molecules that may be present otherwise if you're doing a deposition in a certain gas partial pressure. So you also have a requirement where I gave an example of titanium nitride or an oxide system. You start with aluminum, you vaporize it. If you have vacuum inside the chamber, no traces of air molecules, no oxygen, then you get pure aluminum layer. If there is oxygen present inside the chamber, that means you're not evacuated the chamber to the required levels. So this oxygen from the air can react with aluminum atoms and you get an oxide formation of aluminum. It's unwanted. You're not achieving what you want. That's why vacuum level is very important. So in those cases where but you want to create aluminum oxide from a metal target of aluminum, then you start with by evaporating aluminum, and then you have the presence of the gas inside the chamber. So once you have a presence of gas inside the chamber, the vacuum levels come down, right? The pressure inside the chamber increases. You don't talk about high vacuum in those cases. Now the pressure levels of less than a few millibar ensures large mean free path levels, and this is good for efficient growth process and also for I mentioned critical analysis involving analytical equipment. Right? I mentioned to you yesterday that not only for thin film deposition process, vacuum is also required for most of the analytical experiments involving especially the spectroscopy experiments. And we have also seen that the surface exposure of gases is a very serious matter. So one has to be very cautious. So you clean the substrate and load it, and you expect a good thin film to form on a clean substrate. But then if the clean substrate is exposed to the ambient, and the ambient gases can contaminate the surfaces within no time. And we have seen that typically in the exposure of gases for one mole layer of gases to settle down on a surface, to contaminate a surface, 3.2 nanoseconds is sufficient. Whereas if you have the same surface inside a vacuum of 10 raised to minus 10 torr, the surface can remain clean for almost 7 hours. But you don't normally keep the chambers evacuated down to those vacuum levels. So normally 10 raised to -2 to 10 raised to -3 torr to preserve the surface of a substrate before the deposition is done is fine. So the gas exposure of gases is measured in Langmuir in units of pressure time, and 1 Langmuir is 10 raised to -6 torr seconds. Okay. Now, if you look at the pressure ranges, starting from atmospheric pressure, 760 torr, okay, and 1.013 into 10 raised to 5 pascals, and this is 1 atmosphere. Now, the low vacuum is defined as, in terms of, in units of torr, anywhere from 760 to 25 torr. And this column gives you the value in pascals and atmospheres. That is low vacuum. Okay. Now, the medium vacuum levels are 25 to 1 into 10 raised to -3 torr, 3 into 10 raised to 3 to 1 into 10 raised to -1 pascals. And you have high vacuum, ranges from 10 raised to -3 to 10 raised to -9 torr. You have ultra high vacuum. Well, even though for high vacuum, I've given this range as, the textbook range is 10 raised to -3 to 10 raised to -9. For all practical purposes, high vacuum, say, kicks in only from 10 raised to -6 onwards. Okay. If you want to, again, going back to the example of depositing alloys and intermetallics and, metals, you need at least a base vacuum of 10 raised to -6 torr. So we can take it as there is a intermediate step between 10 raised to -3 and -6 transition vacuum level, and then high vacuum is 10 raised to -6 to 10 raised to -9. And above that, 10 raised to -9, you have ultra high vacuum, 10 raised to -9 to 10 raised to -12. This is where the real challenge comes. In order to get vacuum levels of the order of 10 raised to -9 torr, first of all, it takes time. Second, the system has to be, the vacuum system has to be built in such a way that, there are absolutely no leaks in the system. It should be completely leak proof. This is absolutely important. Okay. So that's where the design aspects of the vacuum chambers come into picture, and it's again designing chambers that can withstand high vacuum levels is a costly process, and also one requires a lot of technique. But it's possible today. When I talk about X-ray photoelectron spectroscopy unit, where you do very detailed structural analysis. So you put your sample, and then you want to look at the, get information about the binding energies of individual elements inside the solid, and to get information about the binding energies, valence states. You don't want the presence of any extraneous gases present inside the system. So the vacuum levels in such analytical tools starts with 10 raised to -9 torr, right? These are huge chambers. So look, as the chamber size increases, the complexity of getting and maintaining high vacuum levels also increases. So that is ultra high vacuum. And then you have extreme ultra high vacuums, where you go down below 10 raised to -12 torr. It's much more challenging. But very interestingly, you know, the outer atmosphere, space, as you go into the outer atmosphere, leave Earth's atmosphere and go to higher altitudes, outer space has vacuum ranging from 10 raised to minus 6 to 10 raised to minus 17 torr. Can you imagine this? This is just amazing. Of course, the vacuum, the moment you reach 100 kilometers above the Earth's atmosphere, right? The atmospheric pressure drops to about 0.03 pascals or so, right? Atmospheric pressure from 100 kilometers drops down to about 0.03 pascals. That is, if you make a quick conversion, it's about a few millitorr, and that means this converts to about 0.03 pascals is about 3 microbars. Look, from 100 kilometers above the ground level itself, you have a pressure drop. You have a pressure of just a few microbars. This is interesting. So the space, the satellites, especially the space labs, the International Space Station, all of them are there anywhere from 100 to 400 kilometers. That's why astronauts that do spacewalk, if they have to repair the exterior of the the space lab, they have to wear these pressurized suits. Otherwise, they're already in a vacuum, right, in space. And because you have a vacuum in space, we are all saved. And I mean, human inhabitation is possible on the Earth because of the vacuum present there, up there. Because you see, you have a continuous explosion of extraterrestrial objects in space, and there are meteoroids, exploding. They're crushing into each other, and thousands and thousands of events taking place every second. Now you see the amount of sound energy that is generated there could kill all the inhabitation on Earth, if not for vacuum, because sound doesn't travel through vacuum, whereas light does. So this vacuum level that is there in the outer space makes life possible on Earth. Okay. Now let's look at the gas transport and pumping. So I have a pumping module, and then going back to this one again, right? Now I need to connect it to a pump. I need to, so if this is my vacuum chamber, I'm using a vacuum pump, and then there are several connectors from the pump into, I said ideally, if the pump is directly connected there, that's ideal situation. There are no additional extensions. But in most of the cases, it doesn't happen. That's ideal situation. Then I'm also then measuring the conductance of this circular aperture, as I told you yesterday, which is 11.7 times the cross-section area. Okay. So the gas transport and pumping, we talk about various gas flow regimes. These gas flow concepts are very important in order to design the gas flow components in a better way. And then you can also modify and appreciate reduced pressure systems. Incomplete understanding of gas flow limitations results in completely less efficient system performance. This is what I mentioned yesterday. You may have a very well-designed chamber, and then you have a good pumping modules, but then the connecting entities in between are not taken care properly. Then you won't be able to achieve good vacuum, sustained vacuum inside the chamber in order to do a thin film deposition process. Yeah, just as an example, if you have a a cheap piece of tubing. In olden days, when I have to connect this one to a vacuum pump, a rubber tube is used. You know, a typical a tube that you also use to connect your gas cylinder to the stove. Okay, even the tubing that is used in gas stoves has improved tremendously in the last decade. So these are basically gas tubes. What happens is a cheap piece of tubing having the same length and diameter dimensions as a diffusion pump. That's a pump. You'll see what diffusion pump is. We'll cut down the pumping speed to half of its rated value. So I have this chamber, I have the pump there, and ideally each pump has a specified pumping speed, right? Depending on the rotations of the inside pump of the rotor. There is a rotor inside each pump, and that the number of rotations determines what vacuum a pump can give. That's what is meant by pumping speed. So you have the pumping speed here, and if we need to achieve the same pumping speed at this level. So that's why I said the ideal situation is to connect the pump here directly. But if you are using an external pipe, right, you may not be able to achieve the same pumping speed at the mouth of the inlet of the pump at that point. Okay, so that's why it's very important to choose the right length and diameter of these so-called pipes and ducts. So we say that the gas flow is set to occur when there is a net directed movement of gas in the system with the use of the attached pumps, right? And what you see here are typically the pipes that are used between a vacuum chamber and a pump. So the one that is shown on the top is a typical rubber pipe, not desirable because rubber pipes always, what happens is, see, you're creating, if you take the air molecules out of the surroundings, right? So the same thing happens here also, because I'm using this pipe to pump air out from one side into the other side, and the right side is the pump side, and the left side is the chamber side. So there is also low pressure created inside the pipe. So this low pressure it can start degassing molecules of the pipe that is basically made of rubber, right? So rubber pipes also, over a period of time, they start deteriorating. They start developing cracks because of continuously you subject the interior to low pressures. And this is, the second one is normally used for the transport of gases that are used for liquefaction and all that. Again, a little hard plastic with, as you can see here, a metal wire wound inside so that the shape is intact. Okay, and you have these rods. Most of the modern day gas flows units are connected via these gas tubes and metal tubes and metal bellows. Much more effective, of course, more expensive. Yeah, these are what are normally used. These are expensive ones, but then they're the required ones. These are called the bellows, metal bellows, high quality metal bellows. If you want to have a clean vacuum without the problem of the so-called degassing, right? These metal bellows have to be used, so different shapes, different sizes, different diameters. Because they're much expensive compared to the tubes that are shown here. Yeah, you see, this is an example of how a metal bellow is connected. They're also flexible, right? And so we have one pump here, there's another pump there. So the conductance that I talked about, I'll go more in detail towards that. There are many conductances in a given system, not just one. Because if the pump is connected here directly, there's only one conductance. But if I have one pump, the pump here, and then a pipe connecting the chamber to the pump, number one, and there's also a primary pump and a secondary pump. They may be connected in series or parallel. So you're increasing the number of conductances, okay? And then there is what is called an effective system conductance. So when gas flow occurs, we need to distinguish different gas flow regimes. And these regimes depend on the geometry of the system, the pressure, the temperature, and also the type of the gas that is used. We talked about the free molecular flow at low gas densities. That means when the gas pressure is low inside a given container or a chamber, we talk about the molecular flow, right? It's like a nice way water flows on a smooth surface without any hindrance, okay? Now, analytical equipment operate within the molecular flow regimes. This is very important, right? You have Auger electron spectroscopy, you have X-ray photoelectron spectroscopy, electron microscopes, scanning electron microscope, transmission electron microscope, scanning tunneling microscope. All these sophisticated spectroscopy techniques and microscopy techniques, they require vacuum where I said the vacuum levels have to be high, which means you're already in the molecular flow regime. Only at high vacuum levels, your molecular flow regime. Here the mean free path, the lambda mean free path, lambda, between the, between different parts is much larger than compared to the dimension of the system, right? So this is important. So from the point where the evaporation happens in a thin film unit to the substrate, if the mean free path is equal to this distance or larger, then the purpose is served. Yeah. So this is a picture of a typical electron microscope. As you can see here, today we have very powerful electron microscopes. I can get electron microscopes with almost atomic scale resolution, right? You get all detailed information about microstructure, substructure, and depending on the accelerating voltage, you get even atomic resolution. So in this, you have scanning electron microscope and transmission electron microscope. So the electrons are generated there at that point by thermionic emission. Again, the old process. The new microscopes are high resolution microscopes. And in these high resolution microscopes, electrons are generated from, these nice pointed nanostructures. So the electron flux density is enormously enhanced compared to thermionic emission from, filaments. So the generated electrons have to be accelerated in this column to the place here where you have the sample. And this acceleration is, as you can see, it's happening over a length of 1.5, 2 meters, right? And so this whole column has to be in vacuum because you don't want to push these electrons towards the sample, which is kept there. And I see now you can also visualize using an optical system microscope. But of course, the image processing leading to magnification of the point where the electrons impinge is seen here. These are only to position the sample, okay? So this certainly requires good vacuum. There's no doubt about it because the electrons are produced, they're accelerated 100, 200, 300 keV. And that also determines the accelerating potential determines the the wavelength of the electrons. Because the electrons that I produce in this process and make them accelerate towards the substrate or the specimen whose microstructure analysis is done, you can do many things here. One is, it's not only imaging, I can also do what is called EDX, energy dispersive X-ray analysis. So when the electron goes and strikes, the secondary electrons give rise to information about the image of the surface, right? You also have characteristic X-rays generated from the surface when the electrons bombard the material. And I can use the characteristic X-rays to find out what are all the elements that are present in the given area that is being tested. This is very interesting. This is called EDX analysis, energy dispersive X-ray analysis. I can also do wavelength dispersive X-ray spectroscopy, wavelength dispersive spectroscopy, WDS. A lot of information. So you can actually, on the area on which imaging is done, you can also map and see what are the elements present, and how are these elements distributed in a given area. Really fantastic. And the third one is the same electron beam can be used for electron diffraction, right? Because electrons have, again, wavelengths of the order of atomic units. So I can also reduce the wavelength by increasing the accelerating voltage, right? The wavelength is related to the accelerating voltage. It's in fact inversely proportional to root of the accelerating voltage. Okay, so you look how many things one single equipment can do. It can give you a deep surface analysis results. It can give you information about the compositional information. It can also give you electron diffraction. So vacuum is a requirement here. See, you have to pump this whole column down to at least 10 raised to -3 to -4 torr. That is sufficient. Okay. Now at high pressure, the mean free path is reduced. Therefore, So therefore, the intermolecular collisions predominate related to collisions with the walls of the chamber. This is the other extreme. At this extreme, when there's the collision happening between the molecules, where at high pressures, low vacuum. At that extreme, you have the viscous flow. So you have molecular flow on the one side, the viscous flow regime on the other side. It happens in these columns and also inside the thin film growth chambers during the growth process, depending on whether you have a complete vacuum or some gas present at a certain partial pressure. So viscous flow is quite complex, of course, compared to the molecular flow. Viscous flow normally occurs when the pressure is of the order of, it's 2 orders less than the atmospheric pressure, 0.01 atmospheres and above. Okay. So at low gas velocities, the flow is laminar, right? That means layer by layer flow. Laminar flow is like that, one layer flowing over the other layer. Okay. At high viscosities, the flowing layers are not parallel to each other, and they start swirling around and are influenced by any obstacles in the way in the turbulent flow region. Okay. And again, go back to the typical fluid mechanics that you must learn. You have, this is a laminar flow. Okay, and this laminar flow is obstructed if you have an obstacle in the somewhere in the flow regime, and then once you have an obstacle, these pressure cavity is developed, right? That's where the swirling happens. It's the same thing with the gas also, gas flow also. Okay. Yeah, laminar flow and turbulent flow. So you also want to make sure that between the point where electrons are generated and the experiment, the specimen is placed, or between the point where the atoms are emanated and the substrate, you want to make sure that there are no obstacles, but this is unavoidable. In an electron column that I've shown, you have all sets of lenses that are there. Of course, the electrons flow through in between those, the so-called magnetic lenses, but you should not have any obstacles in the path of these, the gas flow. Yeah, so this can cause turbulent flow. So the molecular flow, the flow of gas through a vacuum element under conditions such that the mean free path of the gas molecules is considerably larger than the smallest dimensions of the vacuum element, right? And the viscous flow is where the mean free path of the gas molecules is much less compared to the smallest dimensions of the element. Flow may be turbulent or laminar. Laminar only in this case, right? There's an empirical way in which you can understand this. There is a criteria. There are several criteria, but one of the criterion is use this factor called the Knudsen number, okay, which is the ratio of the diameter of the chamber under study in which you're doing the deposition, or the dimension of the long tube that I've shown there, and the mean free path, right? Now, if you look at this plot here, the system dimensions as a function of pressure, you have the vacuum chamber side on this side, right? That is high pressure side, and the low pressure, high vacuum side on the other side. So, no, the vacuum chamber is on this side. That means as you remove the gas molecules from here, you create high vacuum. So low pressure here and high pressure there, because you're removing the gas molecules and conveying it to ambient. So just a quick look at this shows that these are the dimensions. Of course, 10 raised to -5, -3 centimeters are impractical, but then you may be also thinking of very small orifices or tubes through which gas flow happens, okay? All the way to 10 raised to 4 to 10 raised to 7 centimeters of system dimensions, okay? And pressure here, low pressure here, high vacuum, and the low vacuum there. So this is the molecular flow regime here, the viscous flow there, and the transition between the molecular and viscous regimes. So it's easy to understand. This is where the chamber is, right? Molecular flow, you want molecular flow here, and as you remove gas molecules and convey it to the ambient, this is happening through all those, the tubing and the vacuum pump. So on this side of the pump side, you have always the viscous flow. It doesn't matter, but what I want is the molecular flow here. So what this Knudsen number gives you is it's a ratio of D and mean free path. So again, the empirical way of looking at it is molecular flow happens when Knudsen number is less than 1, and you go to the viscous flow regime when Knudsen numbers are greater than 110, and the intermediate flow is between 1 to 110. It's a lot. This range is wide. Alternatively, if you want to express this in terms of proper dimension pressure units, so you have dP times P, dimension times P, pressure. If it is less than 5 into 10 raised to -3 centimeter torr, you're in molecular regime, flow regime. And if this product is greater than 5 into 10 raised to minus 1 centimeter torr, you're in the viscous flow regime. That's it. So, yeah, we can make a vacuum chamber using a normal pressure cooker that you have at home. You take the pressure cooker, remove the top lid, you have a proper O-ring there, you drill a small hole, connect these gas valves, gas connectors, connected to a pump. This is a small rotary pump, and you have a pressure measuring meter. And once you have the O-ring there, you start the pump, you can easily get, evacuate this volume down to 10 raised to minus 2 torr. Minus 2 torr is what you can get with this normal, what is called the rotary pump. We can create vacuum there. Okay, but the same vessel, when it has to be used as a cooker to cook food, the pressure inside is high on the other side, right? But here is an example to show that the same container, I can use it for creating vacuum. So this pump, is called the rotary pump, a rotary pump where you have these rotors rotating anywhere from 1,000 to 5,000 RPM, okay? And that will give a vacuum of 10 raised to minus 2 to 10 raised to minus 3 torr easily. And that's the limit for the rotary pump. Okay. Yeah. So see the top plate there, this is required because that's where the suction happens. And what is required is a good seal. That seal is called the O-ring. It's made of neoprene, a plastic bead that sits there on top of the, this bottom vessel. And that is so when vacuum suction happens, this rubber, contracts a little bit, and that makes it airtight. That's it. Okay. We also have this, I can show you another example of, yeah, I'll get it. Yeah, some more. Yes, you see, this is how a typical interior of a chamber looks like. The small opening there is because you're opening this part to the bottom vacuum pump assemblies. Look, I talked about surface contamination yesterday. So you prepare a sample and leave it outside, and to the naked eye it looks okay, but then the surface always gets contaminated. The best way to preserve those in any of the samples that you prepare for your experiments is you need not always keep it in a big vacuum pump like this, but you can have a small desiccator, okay? It can be made of plastic. Again, it has two parts, the top part and the bottom part. And then once you evacuate it again with this pump to 10 raised to minus 2 torr, and if there is no leak there, the only leak that can happen is from that boundary. Yeah? If that is properly sealed, if the O-ring is of good quality, you can have the vacuum, sustained vacuum inside of this 10 raised to minus 2 torr, even after the pump is switched off. That is called a vacuum, that's called a leak-proof system. So I evacuated to 10 raised to minus 2 torr, and then I switch the vacuum pump off, and I need to see how long the vacuum remains inside. That is a test for the vacuum leak, okay? Yeah, these are big challenges, when you go for larger sizes, more components inside. You see that? This is a typical large size vacuum pump, and you need all these additional connectors for various things. I want to inlet a gas. I want to use a primary pump to get the low vacuum. I want to use a sophisticated higher order pump like turbomolecular pump. So all these ports are required. And I also need a viewport. I want to see what is happening inside. I want to have another port for a thermocouple to measure the temperature. All this adds to the problem of vacuum leaks. You see this. But today, this technology has gone to a real new level. With all these ports, you see a typical X-ray photoelectron spectroscopy technique where you have to create a huge amount of vacuum, 10⁻⁹ torr, looks like that. A deposition chamber looks like that. So with all these additional ports, right, these are all additional ports, right? These are all metals braced to each other. You still get good vacuum inside these chambers. See that? And this is a pumping module, the chamber, and inside which the deposition happens. And also today we have in situ monitoring. You can actually see how the film is growing when the growth is happening. This is the beauty about the today's technology leading to the process where I can actually monitor the crystallinity of the thin film that is growing on top of the surface. Look at this. This is a big chamber, okay? And you see the number of ports there. So that means so many conductances, and it requires 2-3 specialized pumps. And you see there are other modules here, right? Yeah, it becomes more and more complex. Yeah, again, there's a bigger one. Now you see, what you see here is the border between France and Switzerland, where you have this, this beautiful, this is Grenoble in France, where you have this circle, you see. These are the places where you have the beamline facilities, where, you know, synchrotron beams are created for experiments. And these beams go around in these 27-kilometer circles. Yeah. And then you see the inside of these, you know, beam areas. See that? It's all curving. This all goes into the making of LHC, Large Hadron Collider. You see that? The beams are continuously traveling through that in vacuum, and also the magnetic fields at vantage points to bend the beams. Just a comparison of the size of this with a person riding a small vehicle there. Okay. Now, the vacuum leaks, so the leak rates are given in throughput units, Q units, throughput torr liter per second. Again, so you have a chamber, you evacuate it, and for some time, and you know that with a normal rotary pump, I achieve a vacuum of 10⁻⁻² torr. Then I cut off the source, and I want to see how long the vacuum is sustained. That determines vacuum leaks, or how leak tight the system is. The first one is very leak tight systems are said to be having these kind of rates, less than 10⁻⁻⁶ torr liter per second. You call it very leak tight. You can monitor as a function of time. Once I evacuate it and seal it off, switch the pump off, I can monitor how the vacuum leak is happening, because I have pressure meters everywhere, and these pressure gauges tell me how the vacuum is changing as a function of time, and I can determine this vacuum leaks. Adequately leak tight is something of the order of 10⁻⁵ torr liter per second, and greater than 10⁻⁴ torr liter per second is not leak tight at all. I mean, you have to go back and check your system, various ports that I've shown. There must be some leak happening somewhere. Okay, and vacuum leak testing again it's a completely separate field. You need to have helium gas detectors, helium detectors to detect vacuum leaks. Now, so we have the chamber. Now we need to know about the pumps. the vacuum pumps and vacuum systems. And vacuum pumps they belong to two categories. One is the gas transfer pumps. You have the vacuum chamber, you transfer the gas from inside the chamber to the ambient. And the second type is the entrapment pumps. The name itself suggests they can trap gas molecules. So it's a simple gas pump means basically they remove gases from the interior of the chambers from a given volume and convey the gas molecules to the ambient in one or more stages. These are the gas pumps that convey, they remove gas molecules and convey to the ambient in one or multiple steps. And there is also a possibility of condensing these gas molecules or chemically binding them on the walls situated within the chambers that are being, through which the gas molecules are pumped. So, but entrapment pumps can only be used in conjunction with gas transfer pumps. You cannot just use an entrapment pump alone to create vacuum. There are additional secondary pumps in addition to the normal gas transfer pumps. A normal gas transfer pump is what I have shown in the previous slide. A normal rotary pump is a gas transfer pump, right? There's a rotor there. It is taking the air molecules out and conveying it to the ambient. And there are other pumps based on the same rotation mechanism. I'll come to all of that. So the entrapment pumps work in conjunction with gas transfer pumps, but they're very effective in permanently sorbing, condensing gas molecules on surfaces. This is a very interesting concept. Okay, we'll see how these entrapment pumps work, but these pumps are reversible, right? If they're not operated properly, they can be reversible. So, which means that the trapped gases can go back into the chamber if precautions are not taken. Okay. Yeah. So, if you look at the gas transfer pumps, again, they are divided into two categories. One is the positive displacement pump. The other one is the kinetic vacuum pump. So positive displacement pumps, kinetic vacuum pumps. The examples of positive displacement pumps is a rotary mechanical pump, the simplest of any vacuum pump is just a mechanical rotary pump. We can also create a rotating wheel. I can use it and I can use a rotating wheel and create suction from this one. And in a mechanized way, the number of rotations are increased in an effective way, that's all. And they have roots pump, your scroll pumps, all these belong to the category of positive displacement pumps. The kinetic vacuum pumps, they actually are responsible for creating high vacuum. So the displacement pumps create the fore vacuum, the base vacuum, to the level of 10 raised to minus 2 to 10 raised to minus 3 to 10 raised to minus 4 torr. That's all. If you want to go beyond that, you have to go for these pumps. Diffusion pumps, turbomolecular pumps, cryo pumps, all these pumps are basically the high vacuum pumps. And you can also use entrapment pumps. They're very expensive. They work on the principle of adsorption. You also have sputter ion pumps, cryogenic pumps. They're expensive, but then they can be used in conjunction with the normal pumping systems, pumping modules, to create the so-called clean vacuum. So the amount of gas in a pressure volume units flowing per unit time across a specific cross-sectional area, right, is called the throughput. So I have a, so when the gas molecules are removed, I have a throughput there. That I call it Q. And if the pumping module is also pumping some gas back into it, I call it reverse throughput. Throughput is there, reverse throughput is there. So when you're using a deposition chamber with a pumping module, we don't want the reverse throughput to happen. We always want the throughput. The reverse throughput is dangerous. That means you're putting gases back into the chamber. So that's the reason why, depending on the volume of the chamber, you need to determine the exact capacity of the pump so that the pump has enough capacity to create only the throughput and not the reverse throughput. That's why the throughput is often referred to as pumping capacity when measured at the pump intake. So there's also what is called the pumping speed. Pumping speed is the ratio of the throughput of a given gas to the partial pressure of that gas at a specified point near the inlet of the pump. So the inlet of the pump is what everything matters, right? So that's what I said. If you look at the picture at the bottom here, there are two ports that you see there. One is connected to the pump, right? These are two ports. So one is connected to the pump, to the chamber. So it starts sucking air out. The other one, so it conveys, it goes into the pump, and the other one is exhaust. It exhausts out. Okay. Now, so the pumping speed, when we talk about the pumping speed of the pump that is shown there, it is a ratio of the throughput of a given gas to the partial pressure of that gas at a specific point in the inlet. So that's inlet. And when we talk about the pumping speed, which is Q by P, there is a rated pumping speed for every pump, right? So this pumping speed, so the pump is here, the chamber is here, and there is something that connects the pump to the chamber. So obviously, the pumping speed tends to drop, or the pumping speed at the inlet need not be the same here because of this connector. There's a connectivity, there's conductance. Okay. So at the most, you can reach this pumping value, the pumping value of the pump here, and normal calculations show that the pumping speed at this point is half the level of the inlet pumping speed. That's all. Of course, the ideal situation again is, imagine the inlet is straight away directly connected to this one. But this cannot happen. You can look at the size of the inlet there. It's about 1 inch. And the size of this opening here. So you cannot connect here. You need to have connectors. I need to have a connector that brings, so it couples here, and then the pipe has a reduced dimension which connects to the other side of the pump. Yeah. Okay. I think I'll stop there, and we will continue this tomorrow.